Hello, everyone. Welcome to my session. My name is Li Wu. Today, I'm pleased to present our work for performance diagnosis in cloud microservices using deep learning. This is a joint work with Jasmin, Bogatinovski, Sasho, Nedelkoski, Professor Johan Tordsson, and Professor Odej. Microservice is a very popular software or architecture that decomposes the monolithic applications into multiple microservices. This architecture has been adopted to design large-scale applications that runs in cloud computing, edge computing, IoT, etc. Meanwhile, it also being adopted to run service applications in many big companies like Netflix, Twitter, Uber, etc. On the right, this is the microservice running in Netflix. The blue dots on the circles are the microservices, and the blue lines across the centers are the invocations among the services. In general, microservice-based applications are loosely coupled, which means that microservices can run independently, and they can be designed or developed by separate teams using heterogeneous technology stack and communicate with each other through lightweight communication protocols like RESTful API. In general, the microservice-based application is very huge, which means that it consists of hundreds of thousands of microservices with exposing billions of metrics. And to meet the customer's requirements, it will be frequently updated, like thousands of daily updates. So as we can see that in a microservice system, the microservice system is quite dynamic and quite complex. So if there is one microservice gets abnormal, which means that it takes longer time for these microservices to respond the request sent to it. So, and because of the complex dependencies, this anomaly will propagate among the microservices, as we can see, which is shows in the red dots. And the bigger the red dots means the wider effect that it has. So, which means that with only one abnormal microservice, we can get a large number of anomalies because of the anomaly propagation. If we consider the underlying metrics, it will have much more numbers of anomaly metrics. So to get the root cause from this a large number of anomalies, it's quite difficult and is almost is impossible for a human debugging. So in this paper, we would like to address this problem to locate the root cause of a performance issue in a microservice system. So there is many work that's tried to identify which microservices that initiates the performance degradation in the system. But in this paper, we would like to locate a fine-grained matrix that's fine-grained root cause, which includes which metrics that contribute to the service of anomaly. The motivation behind this research problem is that we argue that if only identifying the microservice is not enough for the system operators, because it still takes a lot of time for them to identify which action should be taken just to reduce the outage time. So if we can get a fine-grained matrix, which means fine-grained root cause, which means that we know which matrix has the problem, then it will be easier for the operator to decide the recovery action. So for example, if we identify the CPU, utilization is higher for this microservice. So then the operator can just scale out the CPU resources for this microservice and then fix the issue. So with this fine-grained root cause localization, then it will propose the automatic recovery afterwards. Yeah. So to address this fine-grained root cause localization, we propose a system. Yeah, this is the system overview. In all, we have 4 modules. First, we collect the data from the application level and the system level with our data collection module. And then we continuously detect the anomalies on the response time of each microservice, which will affect the user experience. If there is an abnormal response time is detected, then it will trigger the core print service localization. In this step, we will try to locate which microservice is the that initiated the performance degradation in the system, and it will result in a ranked list of core print services. And then given the core print services, then the core print matrix localization module will try to identify the core print matrix. At the end, we will get a list of the root cause. The key is the core print service, and the values are the core print matrix. So next, I will introduce the details of the core print service localization and the core print matrix localization. To locate the core print service, we firstly construct an attribute graph, which can show the anomaly propagation across the services and the host. So this is on the left is an attribute graph. The age between the service shows the service evocations, and the age between service and the host shows the service deployment, which means that S1 is runs on H1 and S1 calls S3. After that, we extracted the subgraph based on the anomaly detection modules, and we try to compute the weights of the edges and also the node attributes based on the correlation of the relevance metrics of the components or the nodes in the graph. With this computation, we can get a weighted and scored subgraph. Lastly, we applied a personalized page rank into this graph, where we use the node attribute with the anomaly score as a preference vector. At the end, we will get a list of the potential core print services. As we can see, S1, S4 is ranked as the top one, which means that it has the highest probability to be the root cause or to be the faulty service that initiate the performance degradation. So with this step, we can get a ranked list of the core print service. Next, for each core print service, we apply the core print matrix localization. So in this step, we adopt the autoencoder. And the underlying assumption for this method is that the core print matrix should deviate from its normal operation. This is quite straightforward and obvious that if there is an anomaly in one matrix, there should be some deviation from their normal status. And there are 2 main advantages for applying autoencoder in this core print matrix localization. The first is that we can input arbitrary number of the matrix into this autoencoder. So which means that we can include as many as possible simpletons that we observed in the system. And the second, with the autoencoder, we can model arbitrary relationships among the observed matrix. So with the different depths or the non-linearities of the autoencoder. So we trained our autoencoder in normal status, and then we input the observed abnormal matrix of the core print service into the autoencoder. Then the encoder will provide a mapping from the input to an intermediate layer. After that, the decoder will provide inverse mapping that outputs X star. So if there is a very obvious deviations, there should be a large reconstruction errors. So with autoencoder, we can get the reconstruction errors. Next, we detect the anomalies on this reconstruction error. Here we assume that the reconstruction errors follows Gaussian distribution. And after that, we get a ranked list of the core print metrics based on their reconstruction errors. Once once the metric is detected as anomaly. So here, that's the container CPU has the highest reconstruction errors. Then it will be the top one in the ranked list. So with the autoencoder, we can get the core print metrics, and then yes, that's all of our system. So next we evaluate our system in a testbed where we deployed a well-known microservice benchmark named Sasho in a Kubernetes clusters running on Google Cloud Engine. We simulated the user's behavior with our developer, the load generator and the inject force, two types of force into different microservices. And meanwhile, we collect data from application level with STL, node level with node exporter, container level with C advisor, and finally Prometheus scrap all the metrics and then feed to our system. This is an example of the collected metrics when we inject the CPU hog into microservice catalog. And we can see that there is a spike in the response time here, which is marked in red here. And we can also observe very significant deviations in container CPU and node CPU. But we can also observe some deviations in the container network memory or not memory. So here we can conclude that with the anomaly injection, the corresponding metrics will have very significant deviations, but it also affects other metrics. So with our autoencoder, we can get the reconstruction errors for each of the metrics, and we can see that the CPU has the highest reconstruction errors. And meanwhile, node CPU also has a very obvious reconstruction errors. This is because the container CPU utilization spike will also cause the spike of the node CPU as the container runs on this node. Yeah. So this is the results that after we inject different anomalies on different microservices. And we can see that for most of the cases, our method can achieve 100% in precision, and except for orders and the cars in the memory leak. This is because both of these two microservices are computation intensive, and we inject the faults heavily in our experiments, and this fault will manifest in not only in memory usage, but also in CPU usage. So which makes it quite difficult for autoencoder to get the root cause in top one because it violates our assumptions. That's only the core print metric that manifests significantly in abnormal status. Significant observations in abnormal status. So in all, our system achieves 85.5% in precision and 96.5% in map. After we evaluate the effectiveness of the core print service localization, we next investigate whether applying the autoencoder into the core print service localization can improve its precision. So this is the process that we get a list of the potential core print services, and after that we applying our autoencoder in this in the matrix of this core print service, and then try to rank the core print service again. And the result shows that with the calibration of the autoencoder, it achieved a precision of 92%, outperforming 61.4% than the result of graph-based methods only. So in conclusion, In this paper, we provide a system, we propose a system for fine-grained root cause localization in microservice system. We use the graph-based method to identify the core print service, and then use an autoencoder to identify the core print metrics. In the future, we would like to conduct more experiments with more types of anomalies and comparing with other methods. Again, as our system failed to localize the core print metrics when multiple metrics manifest significant deviations. So in the future, we would like to combine the spatial and the temporal fault propagation analysis to cover more types of the root cause. That's all. Thank you for your listening, and I'm ready to answer questions.